Rotational motion. It's something that is completely essential to everyday life. It appears in a variety of different forms, in the humble unicycle and planes and propellers, in Ferris wheels and amusement park rides, or in any kind of sport. The wheel especially is one of the most ubiquitous representations of rotational motion in our everyday lives. Today we'll be exploring Newton's second law, F equals ma, and its rotational analog, tau equals I alpha. Rotational or angular motion has its own set of equations, closely related to those of linear motion. Theta is angular position, measured in radians. Omega is angular velocity, measured in radians per second. And alpha, once again, is angular acceleration, measured in radians per second squared. Knowing these equations is important, however it is more crucial to understand the concepts behind them. First, an experiment of inertia with two disks of the same mass. One has the mass evenly distributed throughout its shape, the other with the mass on its surface. The same distribution applies to the second trial with a basketball and bowling ball. In both, you'll notice that the bowling ball and filled cylinder roll faster than the hollow counterparts. This is because they have lower moments of inertia. The lower an object's moment of inertia is, the more susceptible it is to accelerate. Many objects have different ways for calculating their moment of inertia. However, today we'll be focusing mainly on cylinders. So, suppose we have a cylinder with a mass of 4 kilograms and a radius of 5 meters. Its moment of inertia is equal to 1/2 mr squared, therefore it would be 1/2 times 4 times 5 squared, which is equal to 50 kilograms times meters squared. Then, if we take this same cylinder and want to find the angular acceleration when a force of 50 newtons is applied to the outer edge, you would then set up tau is equal to I alpha, with tau being equal to 50 newtons and I being equal to 50 kilograms times meters squared. And then alpha would be equal to 1 radian per second squared. Then, if we were given an initial angular velocity of 1 radian per second and a final angular velocity of 5 radians per second, we can solve for the torque applied. We use omega equals omega naught plus alpha t to solve for the angular acceleration, and then use the angular acceleration to solve for the torque. Now let's go back to these men on these fantastic unicycles. Let's say one man is on a unicycle going at a linear speed of 30 meters per second. If his angular acceleration is 2 radians per second squared, after 2 seconds, can you figure out how far he's traveled? To solve this problem, you have to know the relationship between linear velocity and angular velocity. Linear velocity is equal to angular velocity times the radius of whatever you have. So, after solving for the angular velocity, then you can then plug into one of the equations you have. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Using that, you can then solve for the position or the angle in radians that the wheel has turned to. Then, knowing the position in radians, how do you find distance? Well, if you know that the circumference of a circle is always 2 pi radians, then you can solve for the number of rotations. Then, if you know the number of rotations and you know the circumference of the circle, you can find the distance that he's traveled. Don't forget to include the units point. Instead of going through all of that trouble, you could also just use the equation x is equal to theta r, multiplying 244 radians by the radius 0.25 meters to get, again, 61 meters. It's important to know the relationships between your angular and linear values.
Ah!